Okay. Let's see. Is everyone here now? Yes. Okay, today we're going to be not talking about color mixing. I just put that here because that's where we ended up last class period. We're going to be talking about more things that have to do with just the nature of light. So, start with a simple question for you. Whoops. Which you can answer starting now. Why is the sky blue? It is here. Okay. I will figure it out. Disconnected properly. Maybe not. It still says disconnected here. Okay, there. So why is the sky blue? Well, you use your clicker. Okay, we've all answered, and we have, can you see that number? No? There's the answers we got. A fairly good cross-section. I asked this question, of course, before we've gone over it because a lot of people have preconceived ideas of why the sky is blue that don't match reality. So here's the actual reason. It's because of what we call Rayleigh scattering, after Lord Rayleigh. What happens is we have light coming from the sun. Approximately what color is the sun? Actually not. It's whitish. The sun is essentially white. And that white light from the sun, if you look at the picture, you see it's white coming in. As it goes through the atmosphere, the atmospheric particles will have the electrons essentially absorb and re-emit the radiation. We call this Rayleigh scattering. And that Rayleigh scattering occurs if you have the scattering centers, the things that the light is hitting, are smaller than the wavelengths of light. So essentially it has to be from atoms or small molecules, such as the nitrogen that makes 79% of our air. And that Rayleigh scattering is much more efficient, so I'm going to put most efficient, at short wavelengths. Now let's recall, what's the wavelength of red light? Okay, 700-ish. I use 750 because that allows me to use the same number for frequency and wavelength. But yeah, 700-ish, that's red. What about blue light? About 400 nanometers. So which of these is going to have stronger Rayleigh scattering? Blue, because it has the shorter wavelength. And in fact, the Rayleigh scattering is proportional to 1 over wavelength to the 4th power. So since 400 is just about 1/2 of 750, I mean it's not equal to, but it's about 1/2. 1/2 to the 4th power is 16. So blue light is scattered about 16 times stronger than red light. So in a general sense, we can say the light started out as white. If it's white, what does that tell you about the colors present? They're all present in roughly equal amounts. Not exactly equal, but roughly equal amounts. But if you take away a lot of blue, what does that leave you with? No, if you take away the blue, what does that leave you with? I have white light, and then I remove the blue. Okay, it leaves you with red plus green, and red plus green we call yellow. So the sun looks a lot more yellow than it really is because of the blue light that was scattered away. Now, don't go looking directly at the sun. That's bad, right? But the sun, we all know, has a yellow color, largely because of the blue light being scattered away. But where does that blue light go? It goes all different directions. So if I look anywhere in the sky that's not at the sun, then I'm doing something like this. I look out here, and what I see is scattered light that came initially from the sun, right? Sunlight came like this and like this and like this. And then I had scattering, and that scattered light had some scattered at the angle, so it comes straight to me. And so when I look at any direction other than the sun, I'm only looking at the scattered light, and thus I'm seeing just the light that was scattered. Not the direct sunlight, but the scattered sunlight. And since scattering is much stronger in blue, I see a blue sky. So what about these other answers? What were the common answers for why the sky was blue? Okay, reflection from water. It's not the reason, but it does beg the question, why is water blue? It's not because the sky is blue. That would kind of be a circular, if both of those were true, it would be a circular argument, right? Why is water blue? There are two things that play with the water. One is there's this Rayleigh scattering as well, but also water has an absorption in the red. And so it takes out red and some green, leaving you with a bluish tint, bluish-green tint. So water's color is more because of absorption. The sky is because of that Rayleigh scattering. Come on, Pastor. Sunsets. When you look at a sunset, what color is the sky? It's red. Red, purple. Interesting colors, right? It's a good question as to why is the sky these other colors. And here is the basic reason why sunsets are red. You have the light from the sun that was largely white. It comes and you start removing the blue, and you remove a lot of blue so that by the time it gets overhead at sunset, it's got to go through a lot of atmosphere. So you have a lot more of the blue removed, leaving a lot more just red sunlight. And that's why we tend to see the red skies, because we see the sunlight then reflecting off of clouds and whatnot, and the light that got to us was primarily red. One last thing on this. When the sun sets, where is it? Okay, we see it on the horizon. That's kind of a different question. I said, where is it? We see it. Okay, in reality, we're really tiny compared to the size of the earth. So we don't see the curvature of the earth. So you see the light coming in like this. If I see the light coming from Joseph and is coming this way, I immediately say Joseph's there, right? So we tend to think that the sun is going to be somewhere out here. But that's not where it is. It's lower. The sun is actually about 5 degrees below the horizon, and the light is bending as it goes through the atmosphere. So when we have sunset, the sun is already set, which is really kind of interesting, I think. Also, have you ever noticed that sunset, as the sun is going down over the horizon, it seems to change shape. It flattens and gets wider. It's because of the same thing. So, interesting things. We wouldn't be in physics class if it wasn't interesting. Okay, pretty picture. Anybody when they were kids like to play with balloons, or not balloons? No. Bubbles, that's the word. See, when a person has Alzheimer's disease, you got to help them out here. I don't believe. Bubbles. We all like to play with bubbles as kids, right? And many of us as adults. And when you play with the bubbles, one of the things you always notice is, ooh, pretty, pretty colors, right?
Yes.
Yeah, okay. Don't make me feel like I'm the only one here. Adulting is hard. So we see those colors, and the question here for physics is, where do those colors come from? Right? Physics, we look at whatever's interesting. You observe something interesting. Remember, on the final exam, you're going to have to go through the scientific process again. So you observe something interesting like pretty colors in the bubbles. What's the next step in the scientific process? Okay, you create a hypothesis, and what are the three things it has to do? One of my biggest goals for this class is for people to not only be able to say these words, but to be able to apply them. That's why it was on the first exam, and it'll be on the final exam as well. It's one of my biggest goals for the class. So, step 3. Test a prediction. That is not how you spell test, it turns out. Of the hypothesis. You do not check to make sure your observation is correct. You're testing a prediction of the hypothesis. And then what's the final piece of the pie? Okay, so if test is passed, then you go back to number 3. You test a new prediction or test the prediction a different way. What if it fails? Got to put it fails. If fails, then back to number 2. Create a new hypothesis, because now you have more knowledge. More knowledge, you know what it's not. You can make a more accurate hypothesis in theory. And as you go through this, you keep ruling out things until, if you remove all that's wrong, you're left with what's right. And how long does it take to get to what's right? You're never proven right. But the more you go at it, the stronger your confidence becomes in it. So this is the scientific method. So let's apply this to our thin film. We observe something interesting. Pretty, pretty colors. Then what do? Okay, somebody throw one out there. Why? Now, I wrote this down. Does that mean he's correct? No. Your hypothesis is basically an educated guess. We took information. He used refraction. We haven't actually talked about refraction yet. That'll be a topic for our final week of the semester. But he took this idea of light refracting, that is light bending. I did show you Newton's experiment with the prism showing that the light separated. And so you know light separates with refraction. So we have a hypothesis based on scientific ideas. Is it going to make, well, of course it's going to make testable things. It's generally hard to make things that aren't testable, but you can. So now we have to figure out a way to test it. Now, I can't think of a great way to test this, mostly because I'm kind of trying to rush because I want to do the teacher evaluation and get back to the conference today. But the next step would be to find a test that could test, okay, is this caused by light refracting when it goes through the film? Because of time and everything, I'm not going to go and try to come up with an experiment, but instead come to what is the correct answer after people have gone through ideas like this and other ideas of what's going on. And it turns out what is going on is when light hits that film, or when it hits a piece of glass, like a window glass, you have some light that reflects off the front surface. That's going to be somewhere around 10% of the light, 5 to 10%. It depends on what the material is. So 5 to 10% is reflected, which means somewhere around 90% goes through. Well, when it gets to the back surface, what's going to happen? You're going to have, again, about 90% transmitted. What's 90 times 90? 90% of 90 is 9 times 9 is. So we have about 81% comes out here, and we have the remaining about 9%, 10% of 90 reflects back. Gets to the back surface. What happens to the back surface? Or the front surface again. We're going to have both transmission and reflection, so we'll have about 90% of 9, so about 8.1% of my original light comes out there in beam 2, and the remaining 0.9% is reflected back. And of that 0.9%, 90% is transmitted, so about, we're getting down to small numbers, 0.81% here in beam B, and we have 0.9 times 0.1 is about 0.09% here, and of that, and so on. So of these, I'm going to have the light, if it's a thin film. This only works for thin films, what I'm describing. If I have a thick piece of glass, you don't see this effect. But if I have a thin film of a bubble, then we see it. Because if it's thin, then these three rays are approximately at the same location. So if I have waves at the same location, what do? They interfere. So I'm going to have interference with these three waves. These waves here will likewise be at the same location, so they will also interfere. Now on this side, 81% and 0.81%, how big of a variation are you going to see caused by the interference? Very, very small variation. What about on the reflected side? 10% and 8.1%. That's reasonably similar in amplitude, so we're going to see big effects there. So we're going to focus our attention on the reflected light because that's where we're going to see the biggest effects. So now I have some light that just straight reflected, some light that had to go through the film and come back and then came out. So they had different path lengths. Since they have different path lengths, that means that they're separated by time now. The light that came in here together, you're out here, when it gets back to here, those aren't going to come back together at the same part of the wave. You're going to have a delay for the longer path. And so what we have to look at is how big is that delay and what effect is that going to have. So as the light goes through the film, it's going to go through change in time is equal to, okay, I'm just not going to use time. I was going to calculate the time for the delay, but this uses the symbol T for thickness. I cannot do a problem with T for time and thickness at the same time. Rather than trying to contrive a variable, I'm just going to go with wavelengths instead of time. You can do it either way. So if we look at wavelengths, how much was the wavelength shift on this reflection? So I'm going to say change in, I'll put change in, we use L for path length, for the length in terms of wavelengths. Well, what was the path length difference from here to here if all I did was reflect? If I have a ball that comes and it hits the table, what's the distance it travels between just the instant it touches the table and the instant it leaves the table? Pretty much nothing. And so that's 0. Now on the next slide, I'm going to make a correction here for certain situations. So I'm saying right now it's 0, but on the next slide I will correct that actually. I'm also going to change the color, put it in green. I'm putting a star here because we know that I'm going to change it on the next slide. Well, this other path, it had to travel through and back. So if it's a distance thickness through, what's the total distance it had to travel? Okay, so this one has delta L2 is equal to 2 thickness. So I have a difference in the path lengths. And now I want to find out how those lengths compare to the wavelength of my light. The first one, well, 0 is going to be 0, right? There's no conversion I need to do. The second one, when light goes from one material to another, we have a basic rule that the frequency cannot change for a wave. So when the light goes through, its frequency has to stay the same, but when it goes into the film, it's going to slow down. We had the relationship that said frequency times wavelength is equal to the speed. If frequency stays the same and the speed slows down, what does the wavelength do? The wavelength is going to have to shorten as well. So the wavelength in the material is equal to the wavelength that I had in air divided by this number n that is an index that tells me how much it slowed down. N is called the index of refraction. It is defined as the speed of light in vacuum divided by the speed of light in whatever the material is. So it's an index that tells me how much it slowed down and thus will tell me how much it shortened the wavelength. And so I am going to say the change in phase is going to be equal to that delta L2, the length, and then I'm going to have to make a correction for wavelength. How many wavelengths is that? Well, it would be that length divided by the wavelength in the material. That's how many wavelengths it would be. So 1 wavelength, 2 wavelengths, 3 wavelengths, etc. And so that's the change in phase for the second one. The change in phase for the first one was just 0. And so now I'm going to have this light coming back together, and I have 2 different phases, 2 different amounts of wavelengths they've gone through. For constructive interference, how much wavelength change should I have? You remember that? Anyone? Is what? What was the phase difference necessary for things to be in phase, to have constructive interference? What basic condition gave us constructive interference when we added two waves? Remember, I drew waves. Here's one wave. Here's, for instance, another wave. Is that going to be constructive or destructive? It's destructive. And how do you know? Okay, they're not timed. When this one is at a peak, this one here is at a valley. They are shifted over by 1/2 wavelength for destructive. And it doesn't have to be just 1/2. It could have also been 3/2 wavelengths or 5/2 wavelengths. All of those would have been destructive. What about for constructive then? What does it need to be? They have to be what? They have to be aligned. Is that what you said? Okay, so they have to be, for constructive, 0 or 1 or 2, etc. wavelengths. Since I have my phi in wavelengths, that's why I put it just 0, 1, 2. And so if I take what I have from above, I'm going to have delta L2 was equal to 2 thickness. Where do I have that written down? Up here. 2 thickness. And so put these two values in to this equation. I have 2 thickness times n over lambda 0 minus 0 equals 0, 1, 2, etc. for constructive interference. And if it was destructive, it'd have to be 1/2, 3/2, 5/2, etc. Now there is, like I said, a twist on this, and that is illustrated by these waves on a rope. If I have a rope and it's attached to a wall, you're going to have the same behavior as if it was attached to a slower medium. That is a rope that's thicker. And if you had the rope tied to a wall, we had the phase flipped. Remember when we talked about that? But if you have it connected to nothing, that's like being tied to a lighter rope, and the phase comes back the same. So that actually changes, the reason I put the asterisk up here, that changes this. At each reflection, I have to add, did it reflect off of something that was slower? If it's yes, then it has a 1/2 wavelength shift. If the answer is no, there was no shift. So going from air to my film, it's slowed down going to the film, so I'm going to have plus 1/2 wavelength because of the reflection causing a 1/2 wavelength shift. Now this one also reflected, but it went from slower to faster. Slower to faster, it would be plus 0. So now I have to correct my equation down here. Plus 1/2, right, divided by the wavelength. And so here, minus 1/2. And so that gives me my final equation for this case. 2 thickness n over the wavelength in air minus 1/2 is equal to, and I'm just going to put m, where m is an integer, and it could be any integer. So the thicknesses that will give me constructive interference are equal to m plus 1/2 times the wavelength in air divided by 2n. So those are the thicknesses that give me constructive interference. Now I have light coming in with all wavelengths, right? White light. So I'm going to have all different wavelengths on the right-hand side. Depending on the thickness, I will have constructive interference for only certain ones of those wavelengths. And so my figure here, whoops, go back a slide. This figure is showing constructive interference for only certain colors based on the thickness. And that's what gives us pretty colors. It's called thin film interference. Cool? Is it easy? Yeah, no, probably not. What do you need to remember from this? You're not going to have to go through the whole derivation, but you need to remember what causes these patterns. Was it our original hypothesis of light refracting through the film? It wasn't refraction. It wasn't bending as it went through, bending different amounts with different colors. It was the interference of light reflected from the front surface with light reflected from the back surface. That you need to remember. And that's why the thickness makes a difference. Why did it have to be a thin film? Why didn't it work with the glass in the windows? They're too thick so that the light is not effectively the same location, and hence it doesn't interfere with itself. You would have those two rays too far apart. It doesn't have its correlation, doesn't work. Okay, now I have two more things to talk about in 5 minutes, but these are way too cool to skip. I didn't bring anything except for these glasses. Have I passed these out before? No? Okay. Make sure you give them back. Actually, I'm going to be gone when class is over, so just leave them on the front table. These glasses are what we call diffraction grading. You can tell from their sweet design that they're designed for kids' parties. If you take them and look at the light, what do you see? Pretty colors. These colors can only occur, just like the thing I just talked about, they can only occur being separated if light's away. What's happening is illustrated on my picture there. I have light going through two different slits, and then I have a different path from the light going through one slit to, in this case, the back of my retina, as I have for the light that went through another slit. Not very different, but it's a little different. And because of the difference in path length, I will have constructive or destructive interference for the light that went from one slit to my eye and the light that went from another slit to my eye. The result is those different path lengths give me different colors that are constructive interference depending on the angle. So it separates the light up into its constituent colors. So like if you look out the window or look to the sides of the window, you just see an ice rainbow, right? All the colors present. But if you look at the light that comes from the lights up above, try to look at an angle, so look across, so look directly above you. What do you see? Yeah, you see a grid of distinct colors. Red, yellow, green, a light blue, and a deeper blue. You don't think about these as a different color as the light coming from the sky, but it is. It's very different because these are made with phosphors to give off specific colors, whereas the sun gives off a continuous range of colors, making the rainbow. So we can see those using the diffraction grading. Another example of interference. Historically, this was super important. Sir Thomas Young did the experiments showing that you could separate light through this interference and thus convinced the world light has to be a wave because only a wave can do this. If it was particles and particles went through those two slits, you would just basically have two places where the particles hang up, light here and light here. But if it's waves, then you can have the interference. Going through the geometry of this, which we are simply not going to go through the geometry because of time. I'm going to skip this question actually because I didn't talk about it. And go to my last piece, polarization. Polarization is another wave-only idea. In fact, it has to be a transverse wave specifically for polarization. Polarization is having the displacement only in one direction perpendicular to velocity. So when I had my slinky or something, when Michaela and I were playing with the slinky. When I did the transverse wave, I was going vertical. My displacement was vertical. So that was a polarized transverse wave with a vertical polarization because the displacement was vertical. The horizontal was the direction of the velocity. But I could have gone horizontal with it, right? That would have likewise been polarized because it was displacement in one direction. If I had gone around a circle like this, so I made it go around like this, that would have been a combination of waves like this and waves like this. So that would be unpolarized. The light coming from the sun is generally unpolarized. That is, the electric fields, remember I said we can talk about electric fields or magnetic fields, either one is sufficient. The electric fields are oscillating in all directions as long as they're perpendicular to the direction the light's coming to you. But using a device like, I can limit so I only have the electric fields coming through in one direction. So I have electric fields in all directions hitting this, but on this side it's only oscillating in one direction. So it cuts out a lot of light. So polarizers can be used to cut off light, and I'm going to use the polarizers for some nifty demonstrations here before I leave you to evaluate the class. So, forget it. Let's just get right to it. Turn in your potential test questions, yes. Is that what you were asking? Okay, so here I have, two lights under here shining through. Got a piece of paper on top. This is a poor man's light source. Light's coming through, no polarizer. When I put the polarizer on, what happens to the intensity of the light? It's going to get brighter or darker? Okay, darker. I'm going to turn off the lights to make things a little more... I know we still have the light in the back. Oh, for pity's sake, let me rotate this so the R looks correct. R for Richard, of course. Okay, so it got darker. Here we can see the difference in the two. Yeah, got darker. In theory, it will be half as bright when I put the polarizer on because the unpolarized light was about equal in all directions. Now I'm going to take a second polarizer. Now let's think about this logically. If I have all the light so it's going in the vertical direction, and I put another polarizer that allows light through in the vertical direction, how much should it block? If I allow through all the vertical light and all the light is vertical, how should it block? None. What if I rotate 9 degrees and I only allow the horizontal through, but all the light's vertical? How should it block? All of it. So let's look at this. Now I have to give it a little light so the contrast stays reasonably constant. So here we can see it wasn't perfect. It blocked a little extra. That's just the imperfection of these things. They always block some. This is aligned together. Now I'm going to rotate it 9 degrees. What's happening as I rotate? So when it's 9 degrees, how much comes through?
Nothing.
Okay. Works just like I predicted, right? Now you can think about this. You might have polarized sunglasses. How many people have polarized sunglasses? Just one. Polarized sunglasses are really useful for things like snow skiing, driving in a bright sunny day, water skiing. Of course, if you wear water skiing, if you fall, you might have some glass in the eye. That might be a problem. But, day on the water. Why? Because glare. When light reflects off of a surface, it actually partially polarizes that light. So like if light comes down and hits this tabletop, the light that was oscillating in this direction is more likely to be reflected. The light that was going like this is more likely to go into it. So you wear polarized sunglasses, and those polarized sunglasses are angled, so they're only going to allow the vertical polarization through. So light that reflected off of a horizontal surface is going to be blocked. So you wear your polarized sunglasses for fishing. Instead of seeing the sunlight reflecting off the surface of the water, you see right through the surface and you can see the fishies. And so what I like to do is driving my car wearing polarized sunglasses, I go, why? because I have the partially polarized reflections off the road surface. And as I turn my head, I'm changing the angle. I'm getting more and less glare, so it's getting brighter, darker. I think it's really cool. Okay, let's look at another couple of really cool things. First, where did I put it? Here. That is just a piece of plexiglass. Really nothing special, right? I put a polarizer on top. Why in the world is it doing that, you ask? It's because the stress in the plexiglass causes some polarization rotation. It rotates the angle of polarization. And so different light is polarized, or the polarization direction is rotated. And so you see cool things by having crossed polarizers with the stressed plexiglass in between. Well, that's cool. We can find other things that do that. So here is a slide that has cellophane tape on it. Put another polarizer on. Kind of cool, right? Different thicknesses rotate the polarization based on the color. Different colors had different rotations. And so I can choose different colors by changing the orientation of the polarizer on top. So since we can do that, we have this, the symbol of Union College, the clock tower. And, okay, I always like to do it wrong first. That's wrong. The moon is not blue on a white sky. But I just rotate it 90 degrees. Ah, there we have a nice white moon on a dark sky with a pretty, pretty clock tower. And finally, hopefully y'all can recognize what this baby is. Okay, wait, got to put it this way. Got to align. I'm looking at the screen, and with the screen, it looked right the other way. Okay. Like I said, I always like to start wrong. Not what my flag looks like. Still not what my flag looks like, but better. Why is this not what my flag looks like? The flag in the country where my brother and sister were born had a single star instead of 50 stars. Why? Because they were born in Liberia. Liberia has a government that was founded by freed slaves, and they modeled many things after the United States, including the Pledge of Allegiance and the flag. What does the flag look like today?
The stars are like awesome.
Yeah. If you count this, we have 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6, 7, 8. 6 times 8 is 48, which means this flag was made like in 1948 or earlier, before Hawaii and Alaska joined the Union. Now we should also count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Make sure we have 13 stripes. That part is good. Now I have one more trick before I leave you. And that last trick is, look very carefully at that R. I'm going to put on top of this a piece of calcite crystal. What happened to my R? It doubled. Now I take a polarizer. I put the polarizer on top. Still doubled, right? Oh, just one now. Rotate 90 degrees from that. There's the... Okay, I rotate too much. I can change between the two with the polarizer. That's an interesting observation. Using the scientific method, the next step would be to come up with a hypothesis Y. What would your hypothesis be? This is my last question, I'm leaving. What would your hypothesis be?
One of the images comes out of different orientation wavelength than the polarizer block.
Right. It must have, the two images were caused by different polarizations. And so, let's go to stop recording.